Okay, so I'm going to jump now because we're really getting to the point where we've got some really good ideas as to why we have some of the shapes that we observe. So now I'm going to jump into a little bit more with dipole moments, and we're going to talk about overall vector dipole moments, or overall dipole moments of a molecule. Now remember with dipole moments, anytime that I had a polarized bond, I could draw this vector arrow representing where the electrons went, right? And here's the positive charge side showing that the carbon is partially positive, and the arrows show where the electrons are going in this polar covalent bond. Well, what that means, right, is that that bond is polarized towards the chlorine because the chlorine is more electronegative than the carbon. So carbon has a partial positive. Well, if we have multiple dipoles in a single molecule, we can get an overall dipole moment, or an overall sum of the dipoles, by drawing what's called a dipole moment on the molecule. And that's using one of these vector arrows to show the polarization of the whole molecule. But that vector arrow is just a vector sum. So if you look at this molecule, we have two vectors that we need to sum. This is done in an incredibly qualitative way. Don't do this quantitatively. We're not doing the math associated with that. That's physics. We're not doing that. We're doing organic chemistry. All we're doing is drawing an arrow that estimates the vector sum of these two arrows. All right, so the vector sum of these two arrows is going to take into account let's say the fact that there's an up and down component, right? And the up component of the arrow here, right? That arrow's up component is greater than the down component of the arrow here. And then there's a left and right component, and there is a right angled component for the bottom arrow that is not canceled out by anything on the top arrow. So when I sum those two arrows up, I get an arrow that looks like this. Again, qualitatively here, I'm just visually summing up those two arrows as there's a vector sum that looks like that. I'm keeping the right component of the one arrow, and then I'm slightly canceling out the up component with the down component of the bottom arrow. This is important when it comes to shapes of molecules. So if you look at water, I can draw water in two different ways. Here's linear water, which is what we might expect if we didn't know anything about shapes of molecules, right? Two hydrogens, push them as far apart from each other as possible. But we know that there's two lone pairs on that oxygen, and therefore oxygen adopts that bent that bent configuration with a roughly 105-degree bond angle between those two hydrogens. That makes a difference because now, right, if I were to draw my individual vectors on water as a linear structure and water as a bent structure, the overall polarization of linear water would be 0, right? There's left and right components only, and those get completely canceled out. Whereas over here in water as a bent structure, the left and right components get canceled out, but water still has a up and down component in terms of its dipole moment, or overall polarization. And that's incredibly important because water is a very polar molecule. And we know water is a polar molecule. And the fact that water is a polar molecule, and it can dissolve salts, right? And it can dissolve polar things like amino acids and sugars, right? And that sort of thing is very important to the fact that you are a water, mostly composed of water, right? You as a human are mostly composed of water. Water has to be polar to have those characteristics. And if water was linear, right, and if we used a very simplistic understanding of shapes of molecules and thought water was linear, right, we wouldn't get that polar component of water, that polarness of water. We know because we get an overall vector sum of 0. But we know that water is polar. We know that because it's sp3 hybridized, that oxygen is sp3 hybridized. Those two hydrogens are not 180 degrees from each other, they're 105 degrees from each other, and that means that there is a vector dipole on any given water molecule, and it's very polar. So anytime you have water, you're going to know that it has more electron density on the top side, on the oxygen side, I should say, and less electron density on the bottom side. And that polarity of water is what gives it all of its life-sustaining properties that we rely on as a species, right, and as a life form. All right, so I've already shown you electrostatic potential maps. I'll show them again, right? They're just showing that the electron density is in red, right, and the lack of electron density is in blue. But they can really give us a sort of more theoretical picture of what electron density around an atom looks like, or around a molecule looks like. So you can see in this case of chloromethane, right, we really have that big polarization, right, of positive charge on the carbon side and negative charge on the chlorine side, as we would expect, given the electronegativity difference between the carbon and the chlorine. All right, so here I have just a quick slide to say that lone pairs contribute to dipole moment. Don't forget lone pairs. When you have a lone pair, that is as concentrated of a negative charge as you can possibly have. So in the space between the nucleus, right, the positive charge, and the lone pair, the negative charge, you have a vector dipole, right? That dipole is, hugely polarized. The electrons are completely negative, and the nucleus is completely positive. So don't forget to draw your don't forget that your lone pairs are going to participate in giving a molecule an overall dipole moment. So in the case of water, right, this existing dipole that we had already set up is sort of increased. Here's my lone pair here. Is sort of increased by the fact that there is also dipole set up between the oxygen and its lone pair. So all of those dipoles sum up to give water a very strong dipole, in that direction towards the, going from the hydrogens towards the oxygen. Okay, so now that we know a little bit of that, we can use two words that we haven't seen yet, and that's electron donating versus electron withdrawing. Now, if you have a very electronegative atom, right, here we know that the electron density is going to be pulled towards the chlorine. So we're going to say that the chlorine is an electron withdrawing group because it's pulling electron density away. Right, so here we've got fluorines pulling electron density away and an overall dipole moment like that. Right, so this is also an EWG like that. Once again, right, here's a carbon or an oxygen with a pi bond, right, and all of this is in relation to the R group here. These are pulling electron density away from the R group, so we're calling them electron withdrawing groups. All right, here we go. Nitrogen, and it's got its own dipole, another EWG. And I'm going to ignore the rest of these for right now. You can go ahead and try to go through them, but we haven't covered one particular topic yet that's going to be important. We're going to need to cover resonance before we really talk about the other ones. We'll come back to this, don't worry.